Okay, so we start from where we left yesterday, and today we are focusing more on factorization. So as yesterday happened, Stefano Forte has already given us a very nice introduction, and he has worked out all the details about collinear factorization. So many things that I will tell you will be more qualitative, just to give you an idea of what happens at the level of phenomenology. Then we will go to consider TMD factorization, which has a few more complications, and we will talk about soft factors, okay? So that's the idea today. Now, again, this is the artificial intelligence idea of factorization. Now, as Stefano has taught us this morning and yesterday, QCD is a very special theory, right? So QCD works in two different regimes where we have to apply two different approaches. One is the short distance regime, where short distance effects are dominating and where we can expand in a perturbative series along the lines that Stefano has actually talked about this morning. This is the realm where asymptotic freedom is at work. And so we can use the elementary degrees of freedom of the theory, which are quarks and gluons. They are the basic objects. We can compute any matrix elements with Feynman diagrams and make predictions, okay? But this is not all, because this is a world where you only have pure gauge degrees of freedom and quarks degrees of freedom, right? Which has nothing to do with the real world that we can experiment and that we can observe, where actually we only see hadrons. We never see quarks or gluons. So for a process to become observable, so in a way for QCD to gain a predictive power, this is what we say in technical jargon. So if you want QCD to gain a predictive power, you also have to face the other regime, which is the confined regime. It's where QCD works the hadronization magics, right? To form hadrons out of quarks and gluons. And this is complicated to treat because no Feynman diagrams work, no perturbative expansion work. And so you have to imagine new ways, invent new ways to deal with this new regime. And this new regime is easy to identify, at least in principle, because it's the regime where distances, scale distances and times are very long, okay? So basically you can always distinguish the two regimes by introducing specific scales in your process, which tell you what is large and what is small, okay? And in what Stefano was doing this morning, these scales are Q squared, for example, or even mu squared, the renormalization scale. We will see that for TMD factorization, we need even more terms for references. Okay, so when you do TMD physics, you basically work at the intersection between the perturbative and the non-perturbative regime. So TMDs crucially contain a perturbative part that you can calculate and what is called the soft part, which is, you cannot calculate it. It's due to the emission of soft gluon. So remember what the questions were this morning about soft gluons. We will go back to that. And this soft contribution to to the theory are extremely elusive. So the soft factor, the soft terms of a process escape detectors. You cannot see them in the detectors, so you cannot measure them. But at the same time, it's very hard to compute them because they're soft, okay? So no perturbation theory holds. And this is the complication that we are going to investigate. One thing that probably Stefano didn't stress enough is that it is factorization which restores the predictive power of QCD. Okay, without factorization, QCD is worth nothing, right? So factorization is actually the tool, it's the scheme that makes QCD operative, right? You can do something with QCD. Otherwise, it remains a theory, a very good theory, very well done, extremely elegant, but useless. Okay. Now, so the ideas of factorization, this is just a cartoon-like explanation. I'll try to be as fast as possible going through these, and then we go in more detail in the second part of the talk. So the idea is that you separate out what is hard, H stands for hard, from what is soft, or we will see soft and collinear. So you need to separate out into a convolution. Remember what we said yesterday, what happens at short time and distance scales, which is the hard part, Feynman diagram, from what happens at larger time, when actual strong interaction can be negotiated between quarks and gluons to generate hadrons. And this is the cartoon for deep inelastic scattering that we saw yesterday, in which a quark scatters with a photon, for example, or the electron sees the charge of this red quark and scatters, and then you have the two particles going on their way back to back in this case. Same thing happens for factorization. This is a scheme which reproduces somehow the semi-inclusive DIS idea, in which not only you observe the scattering between a quark, elementary degree of freedom, and the electron, but you also observe what happens to the scattered quark when it goes over larger, it runs over larger distances, and it hadronizes, okay? So in this case, factorization is separating out not only the hard part from what is non-perturbative, but it also separates out the hadronic structure, the initial structure of the target, from the hadronization mechanism which leads to the final hadron. So this is the PDF, and this is the fragmentation function. Okay? Now, there is another process, together with Sidis and Drelian, there is a third process which is very important, and it's been important over the last, say, 50 years. For factorization and for the study of fragmentation functions in particular. And this is a process in which the annihilation of E plus, of two leptons, typically E plus in minus, leads to the formation of two hadrons, of a pair of hadrons, which are basically almost back to back, okay? And this is this is the cartoon picture of this process. There is a region which is highly perturbative, where the two electrons scatters, and then the electrons do form a Q-bar pair. And if you're sitting in the center of mass, you can imagine that what happens is that you scatter the electrons and positrons, and the two quarks are produced back to back, right, to conserve momentum. Then when you reach larger time and distance scales, there is a hadronization process mechanism going on, and you produce two hadrons. And these two hadrons you observe are not exactly back to back, okay? So it means that basically the hadrons are not produced along the thrust axis, and you can imagine the thrust axis to be, at least at leading order, the axis of the QQ-bar pair. So these two hadrons are produced almost back to back. And what does this tell you? It tells you that there is a transverse momentum going on, okay? So there is a transverse momentum component playing a role here, okay, with respect to the direction of the two parts of the PP bar of the QQ bar pairs. So in this case, the factorization theorem allows you to separate out the hard part, which is this, from the two parts, which are soft in a way, and which describe the hadronization mechanism. And in this case, notice that I've indicated here that the fragmentation functions not only depend on Z, but also on the transverse momentum component of the two hadrons, okay? So in a way, the presence of the small transverse momentum component indicates a deviation from a back-to-back configuration. We went through this yesterday, I think. So it means that there are two vectors now, two more vectors now, which are PAT and PBT transverse. And so the final production of the two hadrons can actually happen in a cone, okay? We are in a 3D space. We've abandoned the collinear approximation that Stefano was using this morning, and the two final hadrons can be produced in a cone, and their azimuthal direction is actually represented by two angles, phi A and phi B. I think I put somewhere. Okay. Yesterday we saw a representation of the actual kinematics. So now, in this, if you want to think about this process in terms of quantum mechanics, for example, you can see the effect of entanglement here, right? Because when the elementary scattering takes place, the spins are entangled. Okay, there is a conservation of spin. And although the spins are entangled, you can take care of these in the TMD factorization proof. And it happens that if you are in 3D, as we saw yesterday, you can have TMD fragmentation functions, which actually take into account the direction of the polarization, the direction of the spin of the quarks with respect, for example, to the polarization or the spin of the final hadrons that you produce. And it is the presence of a transverse momentum component. It is taking into account the transverse momentum component gives you access to the spins as well, okay, through the correlation between spin and transverse momentum. So what happens is that in your detector, as our experimental colleagues know very well and can teach you even better than I can, in your detector, you will actually notice a resulting azimuthal dependence in the final states. And this azimuthal dependence is called the Collins effect, okay? The Collins effect is related to the that TMD that we called H1 perp. Okay, this is a TMD fragmentation functions, which is correlated, it's proportional to the it's related to the probability of producing a spinless hadron, like a pion, for example, out of a transversely polarized quark, right? And I want to stress again that if you didn't have transverse momentum dependence, you couldn't observe this. So this is encoded into this notation. There is a perp here. This means if I integrate these over transverse momenta, which amounts to saying I'm not observing transverse momenta, then this function goes to 0, okay? So this effect goes to 0 unless you work in a 3D space. As I said, experimentalists can measure these, and here I have a collection of experiments in CDs, Compass and Hermes, for example. These are all data, forgive me. I didn't have the time to go through the new plots, and my fault. I will try to update it. And this is for the Collis effect measured in the plus minus in Bell and Babar experiments. And as you see, these data are particularly important because they are mapped in PT, in the transverse component of the final hadron. This gives us a direct access to actual TMD information. Okay. Now, so in a way, always in terms of quantum mechanics, factorization describes a type of decoherence between processes that occur at widely separated location in space and in time. And for it to be possible, you need to have a hierarchy of scales. So in QCD, it's always important to be able to distinguish what is small, which means you can apply perturbation theory, and what is large, okay? Large scale, large times, small energies, smaller energies, and this is the non-perturbative regime. Being able to separate what is perturbative from what is non-perturbative is important because alpha S is only small. You have to know when your perturbative series converges, and it only converges when alpha S is small, okay? Now, there are many ways in which factorization can be broken, okay? And I will go from the mildest to the stronger ways you can break factorization, okay? Factorization theorems are, in a way, process dependent. So in principle, you have to prove factorization for each different process. Andrea Simonelli and I, a few years ago, worked on this factorization breaking mechanism, and we realized that it's not really as bad as a process dependence. It rather involves how many hadrons you have in your process, okay? So if you if you only have if you have two hadrons, you're very well off. If you have more than two hadrons or less than two hadrons, like only one hadron, then you're in trouble, okay? But this is a long story, which I don't have time to go through. Now, as I stressed yesterday, factorization relies on the fact that the observables are very inclusive. You remember yesterday we said we need to sum over as many final states as possible, for example, in DIS, right? Or in CDs. When you make your observable less inclusive, then you start having troubles, and factorization becomes harder and harder and harder to prove until it breaks down. Right, so what is this cartoon? Now, the problem is that when you deal with QCD, you deal with objects which which feature a gauge field, a color field, right? So when you have two hadron scattering or a hadron, I mean, you imagine you have two hadron scattering, and in here you sit from, and you are one of these two hadrons. So you sit in the reference frame of one of the hadron with this one, and you see the other hadron approaching. So what you see basically is only one quark, is the one quark or the one parton which will interact with you, okay? Now, this quark here, which is probably contained in another hadron, but it's not represented here, just to keep the picture clean, goes closer and closer. But even before it has the chance to scatter with another quark inside. It experiences the color field, which is surrounding this other quark inside this hadron, right? So there is a sort of interactions which comes before, which has to do with the fact that this is a gauge field. So it's a color field. And even before interacting, actually scattering, this quark here has been interacting with the color field, which is this light blue area there. And while moving through the field, it's picking up phases, okay, which are highly non-trivial, okay? They are somehow related to longitudinal gluons exchanges, which can happen as initial interactions or even final interactions. So it depends on whether we are considering the initial scattering with the target, with the hadron target, or the hadronization in the final state. So, so this effect, which is actually embedded by gauge links, which we talked about yesterday, is actually due to the contribution of an infinitely large number of longitudinally polarized gluon exchanges, which are responsible for the picking up of all of these phases, okay? And threaten factorization. And in fact, a large amount of work improving TMD factorization is actually trying to find arguments based on gauge invariance to show how a cascade of cancellation happen. So you pick up all these contributions which actually break your factorization. And so you have to make a lot of work to cancel them out, okay? And these cancellation are extremely fine, it's a matter of a fine tuning, okay? We will see how this happens when you make subtractions. So this mechanism goes through subtractions, right? Now, formally in the factorization proof, and we will see this in a minute, these longitudinally polarized gluons get absorbed into something which is a Wilson line. So in other words, all these gluons do pack up in something which within factorization is called the soft factor, okay? Is the soft factor which we were talking about before. It's the hardest part to make reason of when you work in factorization. And the soft factor becomes basically bunches up into a Wilson line. These soft factors, these Wilson lines, in the TMD factorization proof are actually packed into the definition of the PDF or the fragmentation function. So this is very good, but it's extremely dangerous because the fragmentation function that you define in this way is not a purely collinear object as it was in Stefano's proof when you did a collinear factorization, but fragmentation functions or distribution functions become polluted with soft effect, okay, which has nothing to do with the collinear picture that you use to identify your PDFs or your fragmentation functions, right? Where basically the collinear part is just a bunch of very accelerated initial or final partons which are boosted very, very fast. Okay. So basically, Wilson lines account for the fact that a colliding parton must pass through a background field on its way into the collision or on its way out of the collision, okay? And it turns out that whether this interaction happens before the collision. So when the quark is on its way in the scattering region, or after the collision, when the quark is on the way out of the collision just before hadronizing into a hadron, is not the same. It makes a difference, okay? So this is why these effects, which are related to gauge effects in the theories, to the gauge field, the color field of quarks and gluons, can actually break factorization, and they break it in a very subtle way, in a very non-trivial way, okay? This is not new, and we talked about this. This is connected to the gauge link we were talking about, and it's not new in quantum mechanics, and it's a different realization of the Aharonov-Bohm effect for the electric field, okay? I guess you all know about the Aharonov-Bohm effect, but it basically tells you that although that if you make a double slit experiment, but you put a magnetic field, like a very thin solenoid, in a region between the two slits, although the wave function of the two paths cannot enter this area where the magnetic field is different from zero, the two-wave function pick up phases which are different according to the path, okay? And the difference, and what is relevant, as you know, in quantum mechanics, you can never determine what is the phase attributed to a wave function. The only thing that you can measure is the difference between phases in two different wave functions. And it turns out that the difference of the two phases of the wave function going through one path, one slit, and another slit is actually given by this. And this is exactly what in the definition of our TMDs that we saw yesterday is the gauge link, okay? And it is the effect that we were talking about before. So along the way, along its wave, the wave function picks up phases just because a gauge field exists. Although it is far enough not to fill it, and although the field is confined, the phases are topological phases, geometrical phases do fill it, and you can see it. And this is turns out to be proportional to the flux. Okay, so now we saw this yesterday. I'm not going through these anymore, but of course you can find it on the slide if you want to go back to it. Here, this is basically the Wilson line, the gauge link. So the contribution of all the geometrical phases which are picked up along the way. And it's just a tiny little bit more complicated than what we saw before, because here you have the generators of the group that you are considering here. And this is a non-abelian gauge theory. QCD is a non-abelian gauge theory. So these generators have a non-trivial effect. Okay. Now, mild factorization breaking effects due to these can, for example, be a Sievers effect. The Sievers effect is an effect which is related to another, to a TMD PDF, which is the F1T perp. F1T perp is related to the probability of finding an unpolarized quark or parton inside a transversely polarized target, proton, hadron, okay? Now, the Sievers effect results from what I was telling you before. So the amount of phases of the effect of the size of the Wilson line contribution that you pick up on the way in can be different from the size of the Wilson line that you pick up on the way out. Okay, so according to the process, you can have a contribution of this Wilson line which is different. Okay, and in the Sieverts effect, you see these because you realize that the Sieverts effect is process dependent. So if you measure the Sieverts effect in cities, you will find some effect. But if you measure it in the Drellian, you will find something which has got the opposite sign. So in other words, if you measure the Sieverts function, this is the Sieverts function, in cities, and you extract it, and then you measure it in a Drellian process and you extract it, you will find a different sign, okay? And this is due to the fact that in cities, you have a final state interaction. So the Wilson line, the gauge link is at work in the final state when the hadron is produced. In Drellian, this is actually at work in the initial state when the two protons scatter, okay? In Drellian, the final state is clean. You produce a pair of leptons, so you don't see any QCD effect. The first hint of this sign change was measured by the STAR experiment a few years ago. And it's you can see it. Of course, the uncertainties are still large, but you can see here what you predict with using the same, if you get this line, if you use the same sign of the Sieverts function when you measure it in cities, and this is when you change sign. And clearly the data seem to prefer a change of sign rather than the same sign. And then there have been more measurements, in particularly COMPASS, when in the Drellian run has measured also this sign change. And again, you see a plot in which you can see a point here, and this is what you obtain, the predictions that various groups obtained without any sign change with respect to cities. And this is what happens if you change the sign. And again, you have a good evidence that the sign change is there. And this signals the fact that these Wilson line contributions are highly non-trivial, but still here, they are under control. So the factorization breaking is there, but it's mild in the sense that it's under control, and it only introduces a change of sign. There are more nasty factorization breakings, and they usually occur in hadronic processes. So in this case, the Wilson lines are really non-universal. And so basically what happens is that you cannot define Wilson lines which have the same properties. Each Wilson line represents an accumulation of phases as a parton passes in or out of the hadron collision, but they are non-universal. So basically each Wilson line is different from the other, and they depend on the process and they depend on the hadron that you are producing, okay? And this is a much nastier breaking of factorization, which is not under control, okay? So this is why there is a question mark here. So the question is, does this kind of factorization, which you can imagine when you have two initial hadron producing to final hadron in your process? And the answer is no, And the proof of this is highly non-trivial, but I'm just trying to outline what happens in this case. So if you consider this process at leading order, you imagine you exchange a colorless particle in the T channel. So the particle which is here, you can't see it very well, but this is a dotted line. You imagine these two hadrons are exchanging a colorless particle in the T channel. Okay, so if you imagine this process at tree level, you basically can only exchange a quark. Okay, and then a quark, of course, means a color flow, but because the two ingoing quarks are exchanging a colorless flow, you cannot have any color flowing here, and so the color flux is rotating in this way from the initial to the final state, okay? So this is fine. Now, if you imagine to go to higher level, then you start exchanging gluons. And these are the longitudinally polarized gluons that I was talking to you about. They are the gluons that you usually sum up into the Wilson lines, but the gluons are colored objects. They carry color and anticolor, right? So the gluon exchanges which go on here forces you to have a flux of color, a non-trivial flux of colors going from the lower part to the upper part. Lower part and upper part are the structure of the two initial hadrons, okay? So in this particular case, when you have a gluon exchange, you are prevented from factorization simply because you cannot separate the flux of colors from one side with respect to the other, from one hadron with respect to the other. So a configuration like this, in which you can separate out in a convolution a color flow of one kind, red, say, on one side, and a color flow, say, blue on the other side, is not permitted because in QCD colors have to, gluon have to carry two different colors, okay? So you are prevented to separate out the color, the gauge color fields, if you want, in the two different parts, and factorization breaks, okay? So this is just a cartoonish picture to show you what happens. The proof is actually quite complicated, but the basic of the proof is this, okay? It's because QCD is a gauge theory which is non-abelian, and so everything becomes much more complicated. Okay, so we saw that the key concepts of factorization, let me just check what time it is. Okay. So the key concept of factorization is that you take an observable, like a cross-section, say, and you separate out into three different parts. One is the hard part, which means perturbatively calculable. High energy, small distances, small time scales. You can do a perturbation expansion using the coupling constant, which at large energy, large scales, is very small, okay, and everything works out. And you have to be able to separate it out from everything else, and everything else has to do with hadronization, with the confinement region. There are two different parts that you see here. One is the soft part, and one is the collinear part. You can have as many, you do have as many collinear parts as hadrons you have into play in your process. Collinear parts are PDFs, TMD PDFs in our case, because we want to do collinear factorization. Okay, so for example, in CIDIs, I have an initial target, hadron target, and I produce a final hadron. So I have two collinear parts, okay? Then I have a soft part. Soft part, this is usually called the soft factor. The soft factor is a bunch of soft, so low momentum gluons, which are exchanged in the process, and they sort of mix everything up and makes it very, very difficult to separate all parts out. So in a way, this is well defined. This is well defined. The collinear parts, as I said, are bunches of very strongly boosted particles which move in a very precise direction. Okay, usually they define the light cone direction. You put them into either the plus or the minus direction. Whereas the soft part is a bunch of soft gluon, which are correlating. Typically, they are easy to separate out from the hard part, but they cannot be separated out from the collinear parts. So basically, soft gluons are correlating all the soft parts in your process. I have a picture that I can show you, but it's somewhere else. So I'll show you later on. So the problem in the factorization strategy is how to treat soft and collinear contribution, which account for non-perturbative effect and which tend to mix up very badly among each other in a way which is not trivial to treat. So basically, the difficulty is to separate out the actual TMD, which you would like to be purely collinear, from the soft part. And to do this, you use a mechanism which is called subtraction. Subtraction is something that Stefano has already pointed out to you this morning when he was saying if you can subtract out the bare part of AN, okay, from what you actually measure, okay, to renormalize your theory. And this is the same idea. So basically, you want to define your TMD in a way that is subtracted. So you want to subtract out the soft factor. Okay. Now, let me not dwell on this because we have already mentioned what the strategy is. I just want to stress out again that the idea is to separate out what is perturbative, but everything that is perturbative is typically process dependent. So the perturbative part, the Feynman diagram, is something that you can calculate, and you can calculate at any order, provided you're smart enough. You can decide the order you want to calculate it, and you can compute it. But you have to do it again and again when you change process. So every time you consider a different process, you have to compute it again. Instead, collinear parts are TMDs or PDFs in general are universally. So, are universal. So they are deeply non-perturbative. You cannot calculate them. But if you extract them in one process, you can use them in another process. And this universality is the only weapon that we have, okay? And we have to use it very carefully, right? So universality is something you really don't want to break, because if you break universality, then there's nothing you can say, right? You can have as many experimental information you want, as many data as you want, as accurate and precise as you want, but if you break universality, they will be worth nothing because you extract something from one process and then you cannot use it into any other process, okay? Okay, so the strategy of factorization, TMD factorization, is locate, classify, and separate. Locate and classify are procedures which are based on a strong hierarchy in the scales. So you can only do these if you can separate out what are called the relevant momentum regions. And the relevant momentum regions are regions in which momenta have all large components. Okay, so what is hard? Hard is what has any vector which has any momentum which has all other components very large of the size of the scale Q. Okay, then you have the collinear regions. And collinear means you do have one large component. So there is one direction which you can identify very well, okay? In fact, the collinear part is, as I said, a bunch of particles being boosted very fast into one direction. The other components are soft, okay? One is of the scale lambda, which is a small scale. Lambda can be lambda QCD, for example, 300 MeV, whatever you like, whatever is small in your process. And the other one is even smaller because it's lambda squared divided by Q, okay? And Q is very large, it's a large scale here. And then you have the soft region. The soft momentum region is characterized, and these are the momentum that characterize the soft part of the process, the soft term of the process. These are momenta in which all the components are small. Lambda S is actually lambda squared divided by Q. Okay, so it's not only lambda, it's lambda squared divided by 2, which is even smaller. Okay, so there are a sort of momentum classification. You do this power counting, which allows you to separate out these kinematic region, these momentum regions, and this is fundamental. Once you're there, you of course you associate the hard part to what is connected to a large virtuality. The virtuality is actually Q squared, and you compute this with a Feynman diagram. So that part is easy, okay? And each there is something which is not written in these slides, but it's very important. When you do factorization, you work with approximator. This is something that John Collins introduced in 2011. And these approximations are operators which actually allow you to operate the right approximation for each momentum region, okay? So basically, these approximators are the operators which allow you to do the actual separation. Okay, so you first separate out the hard part, and that's the easy bit. And then you have to deal with the part which is connected to low virtuality, so low momentum components. And what you want to do is to separate out the collinear and the soft part. The collinear part is actually encoding the essence of the TMD. The collinear part is describing the hadrons coming out or coming into your scattering process, whereas the soft part are actually encoding the correlations among the collinear parts. And remember, the collinear parts can be more than one, okay? Actually, if they're not more than one, it's even more complicated. Okay. So now we go back to what we were saying before. The complication is about these longitudinally polarized gluons, which are soft, and that you can bunch up into what you call Wilson lines, the gauge link. And you need to take into account the soft radiation. The soft radiation here is what gives you the crypts, because, you know, Stefano was very careful this morning saying, I am not considering the case in which the radiated gluon here is soft. So his momentum is very small, because otherwise I get into trouble, because KT going to 0 and blah, 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 okay? In here, you cannot avoid it. So when you do TMD factorization, you have to deal with this. And you have to deal with soft collinear radiation. And if you work in what is called resummation in the collinear part, then you have evolution equation and all the resummation of towers of logarithms which are connected to the Q evolution. In here, we deal with these Wilson lines, okay? And they are represented like this. So the idea is that you have to take into account a bunch, while your quark propagates, it can emit a bunch of very soft gluons. So anytime, you know, as it moves forward, it actually radiates out soft gluons, low energy gluons. And the way we deal with them is to separate all of this contribution into the convolution, the product of two terms. One is the pure quark, okay? And the other one is the bunch of soft gluons, which we put them, which we collect in the Wilson line, right? With these forms. This is the gauge link or the phase, which in the Barabanov effect you accumulate as the quark moves into the color field of the other part. Okay, so we said this. Let me just check. Yeah. Now, once the factorization is proven, the goal is just to determine the universal non-perturbative contribution separated out by the factorization theorem. And one possible strategy is using, for example, experimental data to extract the TMDs, the PDFs or the TMDs. And so at this stage, once you've separated out the collinear part, you can define your TMDs for the initial state. And this is the table we saw yesterday, where here, for example, we have the series function. Okay, this is after you've proven factorization, you can show that actually your TMDs are nothing else but the Fourier transform of this matrix element, okay, with the Wilson line in between, which guarantees gauge invariance, color gauge invariance. And the same thing you can do for the final state correlation matrix. Again, it's a quark-quark correlation matrix, and this is for the TMD fragmentation functions. Okay, so this is the definition we saw yesterday, and here you have all the possible 8 fragmentation functions, and I remind you that we usually, up to now, concentrate mainly on D1 and H1 perp. This is the Collins effect that we've seen before. And this is the unpolarized fragmentation function. Okay, now there is a caveat in the proof of factorization, and the caveat is that it has been proven for CDs, Drell-Yan, and a plus and minus annihilation into 2 hadrons. So in these 3 benchmark processes that have been, in which you can use, you can prove factorization, you always only have 2 hadrons. You have exactly 2 hadrons. No more, no less, okay? So in a way, the factorization proof is somehow related to how many hadrons you have in your process. And if you change that number of hadrons, the proof doesn't hold anymore, okay? And you have the violation of factorization that I showed you before, for example, for the hadron-hadron scattering resulting in the production of a pair of hadron, of 2 hadrons. So it's a little bit delicate because you have different factorization theorem according to how many hadrons you have, and also you have to take into account that according to the kinematics, you have 2 possible different factorization theorem. One is the collinear factorization, which Stefano has proven this morning, and the other one is the TMD factorization. And again, TMD factorization has to be used when, in particular cases, when the transverse momentum has to be taken into account and cannot be forgotten or approximated to be 0, like in collinear factorization. So I have a slide here in which I just show you the comparison between collinear and TMD factorization. Okay, it's just concepts. There's no no deep and intricate calculation, but I think if you know these, then you can get along pretty well in the field, and you have the basis to reproduce the calculation yourself. So collinear factorization holds when Qt is much larger than Q. So basically, it holds anytime you produce a particle which has a hard, large transverse momentum in the final state. For example, here is imagine you have CDs. So the transverse momentum is large enough to produce a jet at wide angles in the final state. That is typically the hard scattering, okay? You have a process in which you scatter something and then you observe one or two final hadrons with a very large transverse momentum, okay? Wide angles. In this case, the transverse momenta are very large. So low transverse, the effect of low transverse momenta, the transverse momenta, if you want, that are produced by emitting a bunch of soft gluons. So if you, while your quark propagates in the way out, for example, of the process, if it emits soft gluons, it acquires, at every emission, it acquires a very small transverse momentum. It gets a little kick, right? Because of the emission of the gluon. But because the gluon is soft, this kick, this KT which acquires is very small, okay? Because the gluon is soft and you have to conserve momentum. So if the quark, for example, emitted is very energetic and it's got a large transverse momentum, then these little kicks, which you then bunch up into the soft factor, are irrelevant. You don't see them, okay? Because its final transverse momentum is so large that you can, these kicks are negligible, you don't see them. So this is the realm where collinear factorization works. Okay. And the fragmenting pattern, the soft radiation effects are totally negligible. So in this case, if you do the actual computation, you see that the soft factor becomes trivial, and when you integrate, it becomes unity. It becomes equal to 1, okay? It's the identity operator. So there are, the soft factor doesn't play any role. It's not a problem. The hard jets are included into the hard part, while the PDFs are just the collinear part of the process. So the only terms that really encode the non-perturbative effects are the collinear factors associated with the target and the one associated with the detected hadron. And you have PDFs and fragmentation functions, collinear PDFs here and collinear fragmentation functions here, right? So no effect from small transverse momenta, no information on transverse momentum on TMD physics. So no information on the intrinsic transverse momentum. And the form of the factorized cross-section is this one. When Qt is much smaller than Q, then the production of hard jets with high energy is so strongly suppressed. You don't have enough transverse momentum to produce any hard large angle pattern, right? So you become very sensitive to the effect of the soft radiation. You become very sensitive to all the tiny little kicks that the quarks gets when each time it radiates a soft factor. And this is TMD physics, okay? In this case, collinear factorization doesn't hold, the situation becomes much more complicated, and there's nothing is trivial anymore. So the soft factor has to be taken into account, and it becomes the vacuum expectation value of the Wilson lines. Okay, so the soft factor is defined as the vacuum expectation value of all the Wilson lines that we have seen before. Whereas the hard part accounts only for the virtual radiation, so for the radiation of very hard gluons. Now we not only have the collinear factors associated with target and detected hadron, but also the soft factor. And the soft factor doesn't integrate to one anymore, okay? So it's there, it's relevant, and it's actually mixing up, it's correlating all your collinear parts, okay? So it becomes relevant and difficult to take into account. So what is the form of your factorized cross-section now? You have the hard factor, okay? These J indices represent the flavors and colors of the partons which participate to this elementary scattering. So you have the hard part, you have the TMD PDF and the fragmentation function, okay, as before. But in this case, you have the soft factor, and you cannot get rid of it, okay? You have to deal with it because it's in the way, and it doesn't go away. It doesn't cancel out. So that's the most general form of a factorized cross-section in the TMD picture. Notice that here I have written that the dependence of the TMD PDF and on the TMD fragmentation function, not on the transverse momentum, but on BT. And BT is the Fourier conjugate variable to KT in the coordinate space. You know that in quantum mechanics, you can equally use the configuration space or the momentum space. And you move from one space to the other with a Fourier transform. Now, it turns out that in your cross-section, you always have, Feynman tells you that in any cross-section, you have to conserve momentum, okay? The total momentum has to be conserved, and also the momentum in each vertex has to be conserved, or in each loop that you go through. So it turns out that in this case, it's easier to conserve momentum, to keep track of conservation of momentum emission by emission in the, in the picture I showed you before for the soft factor. You have to conserve momentum in each single vertex for each single emission of gluons. And it turns out it is much easier to do it in configuration space, okay? So this is why most often you will see us working in the configuration space, in the BT space, rather than in the KT space, okay? This is just a technicality, and you know that you can also go from one side to this, from one space to the other by a Fourier transform. So in principle, in theory, no problem. I can Fourier transform my functions any way I want. But in phenomenology, this is very complicated because keeping track of KT is already difficult enough. But when you have to keep track of the BT dependence of your function, which you don't see, you have no hint whatsoever from the experiment, is very complicated, okay? So if I have time, I'll tell you something about this tomorrow when we talk about phenomenology. So the question here is, if Jennifer was sitting there like yesterday, I bet she would stop me now and say, what is a soft factor? Give me an idea. How do I imagine a soft factor? Okay. And on this slide, I try to give you an idea. So imagine you are a soft gluon. Okay, so you sit there in the process and you are correlating different collinear parts in your process, and you're very soft. So you have little energy, you're very slow, you're sort of a sleepy gluon sitting there, and you observe the collinear parts of the process, which scares you a little bit because they are very fast, they are very strongly boosted. Okay, so from the point of view of the soft gluons, each collinear group is simply a bunch of particles strongly boosted in a certain direction. Remember that we work in light cone coordinates, so each collinear part, which represent on a long distance scale the hadrons, which are, for example, produced in the final state in E plus E minus annihilation, okay? They are just a bunch of particles which fly away very, very quickly out of you in a specific direction, okay? And this direction is a specific direction which characterizes the observable in your process and the collinear part. The boost of this particle is so strong that the soft gluons cannot see exactly what happens for the collinear parts. The only thing that they can see is the color flow, okay? So there is a color flow, which is the only thing that you little sleepy gluons almost sitting, standing still, can feel of what is going on around you, okay? Because you're so slow and your energy is so small that you don't have the time to pick up any of the details of the collinear part. But you feel the color because you are a gluon and this is your job. A gluon is there to feel the color in a gauge theory. And of course, because you're sitting still, you sort of have an idea of what are the directions of the collinear part because they're very boosted. They're very they're collinear, so they're sort of focalized into one specific direction. So in this sense, the propagation of the collinear particle is well approximating by a Wilson line, and a Wilson line is this, okay? Is usually represented by a double line. And you have Feynman rules for these Wilson lines, and the Feynman rules are here. So you have propagators, which are 1 divided by k dot n plus I0. So 1 divided by k dot n, which is what Stefano mentioned here, okay? And of course, because you have a pole here, you want to tilt it slightly towards into the imaginary plane. And also for Wilson lines, you have a vertex Feynman rules. And of course, you associate to the vertex the G0. So in the massless limit, the versor, which identifies this direction, is light-like. As Stefano was saying, k squared is 0. But the fact that this versor is light-like, and Stefano mentioned this morning, brings troubles. And the troubles are that you have rapidity divergences, okay? Which you have to take into account and you have to try and cancel out. And the way we cancel out these divergences is usually by introducing a rapidity cutoff, okay? So your integrals are diverging, but if you integrate, if you introduce a cutoff, you can regulate the divergences and then you can take the cutoff to 0 or to infinity according to what you're doing. So in collinear factorization, as Stefano was saying this morning, the problem is solved by itself and the soft factor becomes trivial, it integrates to 1 and it just goes away. It doesn't take any troubles. There are event shape observables, like thrust, for example, in which also the divergences are there, but they are sort of naturally regulated. They take care of themselves. In our case, however, in TMD factorization, this is problematic. So, first of all, what is rapidity? Rapidity is this y, defined here, and it's 1/2 of the log of k plus plus k minus. And k plus and k minus are the plus and minus components of the momentum of the gluon, k, okay? This one. Okay. Now, the problem is that if you have something which is strongly boosted into one direction or the other, these ratios are not well defined. And so what do you do in this case? Then you, as we said, you introduce a regulator. And basically, what Collins proposes to do is to tilt the Wilson lines. So the Wilson line, we said, are lines which are very strongly directed into either the plus or the minus direction, okay? And Collins says to regulate the rapidity divergences, we tilt the Wilson line, only very slightly, okay? So they're not along a plus or a minus direction anymore, they're tilted, and they're tilted in different ways, okay? And the way they're tilted is this. So for example, in this case, when you only have one strong boost into the plus direction, you tilt the minus direction slightly in this way. You introduce a regulator, a cutoff, which you then, at the end of the day, will take the limit to infinity. So if y1 goes to infinity, this is e to the minus infinity, which comes back to 0. Okay, so this is the way you regulate your divergence, and for the plus direction, for the minus direction, you do the same here. Okay, so y1 and y2 will be taken to plus infinity in this case and minus infinity in this case. Okay, so by taking this limit, you push back your Wilson line to the original direction. Okay, so this is the way you regulate these dependence. And what happens in the proof of TMD factorization is that the dependence on rapidity cutoff is canceled out in the final result. So what you're doing is a good regulation, because you do your business, you regulate the infinities, but then when you take out the cutoffs in the infinite limit, you get something which is finite, and the cancellation works. Okay, so we said there are 3 processes in which this works very well. In TMD factorization, you have the soft factor, you have to deal with the soft factor, and the way you regulate it is using a cutoff, and you regulate by subtractions, okay? So how do these subtractions work? Basically, you start from here. This is the definition of the factorization theorem. And let's consider just a fragmentation function. I could have used this one, but it's just to give you an example. So let's concentrate on this TMD fragmentation function. How do you define it? You take the unsubtracted part, you divide it out by the soft contribution. The soft contribution is the soft part which is connected to the Wilson line with these longitudinally polarized gluons being exchanged in the gauge fields, okay, for this specific collinear part. So each specific collinear part has its own soft part, which is one of these coming from one of these two approximations, okay? And you subtract it out. And this is what gives you, and then you take the limit to minus infinity, for example, okay? When you take the limit to minus infinity, the cutoff disappears and the cancellation work nicely, and it gives you, it defines a finite object, which is your TMD, okay? But then this is a bit of a catch, because while this is purely collinear, when you divide out by the soft factor, this becomes a mixed object. So in a way, the collinear, the TMD is not just a purely collinear object anymore. It contains some part of the soft factor, okay? And it's polluted by some soft contribution, which is not ideal. We use it because it works, but it's definitely not ideal in principle. And the soft factor is, as I said before, is defined like the vacuum expectation values of this Wilson line with a very specific path, which leads from minus infinity to minus BT half, and then from minus BT half to BT half, and then from BT half to infinity, okay? Now it happens that if you only have two hadrons, so in CDIS, in Drell-Yan, and in plus minus, in the double hadron pair production in E plus minus, the soft factor of the process is the same as the soft factor of the subtractions, okay? And so you can combine them and reshuffle them in a way that they cancel out. And this is what you do. This only happens for these processes, though. So this is your cross-section, okay? It is factorized in this way. You have fragmentation function, fragmentation TMD function, TMD PDF, and the soft factor in between. And here it says 2H. It means that this is the soft factor computed in a process in which you have two hadrons, either two in the initial state, Drell-Yan, two in the final state, E plus minus annihilation, or one in the initial state and one in the final state, like in CDIS. In this particular case, you can recasting the terms in such a way that you take basically this soft factor, you take a square root, and you include the soft factor, one square root on one side and one square root on the other side. So basically what you do is what I said before, you are polluting the definition of your TMD with a soft factor. The TMD is not purely collinear anymore. It's not a collinear part anymore. It is a collinear part in which you push in some contribution from the soft factor, okay? So you separate out and you attribute one square root of the soft factor on one side and one square root of the soft factor on the other side. Now I'm cheating a little bit. It's not really a square root because the functional shape of the soft factor is the same, but the regulators, the rapidity cutoff combination is not exactly the same. So what comes out, what you have to do is you define your TMD. This is called the square, sometimes it's called the square root definition. You define your TMD like the unsubtracted collinear part divided out by the soft factor contribution and multiply, and you have to take the square root and multiply out the soft factor for the process. Okay, and you cook up something which is much dirtier than what you would like, but at this stage you are able to separate out a cross-section in which the soft factor is not there anymore, like in this line. Okay, you only have the hard factor, and then you have a TMD PDF and a TMD fragmentation function. Okay, the soft factor is disappeared. It's not disappeared really. It's just that you pushed it into the belly, into the definition of F and D. You see what I mean? Now, these two depend on a different way from the regulator, Y1 and Y2. But when you take the limit, Y1 and Y2 go into plus and minus infinity, they disappear. And so these cancellations work out, okay? But these, again, this only happens when you have two hadrons in your process, and then you're lucky enough to be in the situation in which the soft factor of the process has the same functional form of the soft factor of the subtractions that you need to regulate your collinear parts, okay? So this is what we are using now, and we did 15 years of phenomenology. These kind of factor, this scheme for the TMD factorization was published by Ted Rogers and Murtai Bhatt in 2011, more or less in the same year the book by Collins came out. It's the red book that I suggested you yesterday. And in that book, Collins actually explains at length all the technical parts of this process, okay? So is everything clear? Do you have questions? Yes, they are universal. They have a degree of universality which preserve some process dependence. And the process dependence is related to the number of hadrons, as I said. So they are universal in the class of hadronicity that you're considering. Okay, so if you stick to the three bench processes which we talked about, the plus and minus annihilation with the production of a pair of hadrons, series or Drell-Yan, then yes, they're universal. So it's true that you put them, you force them inside the definition of the TMDs, but if you extract these TMDs from those three processes, the TMDs will be the same. They are universal, okay? And what I wanted to show to you is that, this is what I told you. Right. So there are processes in which we have a wealth of experimental data. Very nice, very precise. There is a data analysis there are data from Bell. Bell is an experiment with huge, fantastic statistics, okay? They have made a very special analysis in which not only they show basically the cross-section they measured as a function of PT, but they also take into account the thrust dependence, okay, which is useful. However, these data are extremely difficult to analyze because they refer to the production of only one hadron, okay? And this breaks universality. So the function, the fragmentation function which you define, which you can measure in this process is different from the function, TMD fragmentation function that you measure in another process, okay? And Andrea and I have studied this now for quite a number of years, and you have to do some acrobatics, you know, amazing acrobatics to come to terms with this. You have to reinvent a factorization theorem. You have to prove it. You have to do the region separation, kinematics in a completely different way. But we believe we proved that although the fragmentation function that you measure in this process is different, there is a relation which connects this new fragmentation function with the universal fragmentation function. And if you are smart enough, and it's not easy, but if you're smart enough, you will we hope to be able to make to bridge between these two in the next few years. I mean, it's highly difficult, but we have some hopes for that. Okay, so this brings me to my last slide, and here I just want to point out. So this is the drawings that I was talking to you before. So the soft part connects different collinear parts, okay? And it's different. It depends on the process. So CDs and double hadron production in E plus E minus, for example, turn out to have the same soft factor. And this is already rather non-trivial because the way, first of all, the number of collinear parts is different here and here, okay? And in this case, the connection happens between initial state and final state, whereas in this case, the connection happens between two different final states, okay? But it turns out that this bunch of soft gluon boils down to the same soft part for these two processes, okay? Here, it's completely different. Here, basically, what you're missing is you don't know basically how the soft part is behaving in the case you don't have an hydronization on this side. Okay, so soft gluons are negotiating the interaction between the final hadron, which is being produced here, and whatever is not observed, right? And so this makes the details of the soft factor different in this case, right? So we have, just to summarize, we have seen different cases of factorization theorems. And we have seen cases in which the factorization theorem works, and it works really well, but it works in a highly non-trivial way. And it works based on some very subtle cancellation, which only happen if you're particularly smart and if you're particularly lucky, okay? And then we have seen a few examples in which factorization does not work. Factorization breaks. And in some cases, the factorization typically it breaks because of QCD being a non-abelian gauge theory. So you have contributions from the gauge color field, which are highly non-trivial. But sometimes you can sort of find a reason. The breaking is there, but it's mild and it's under control. And some other times, the breaking is really nasty, it's really bad, and there's no way you can just find a way to deal with it. Okay? Okay, is there any question? Mm-hmm. Yes, it's a soft factor. And as I said, the idea is that you take this structure, okay, and you break these into two parts, and you give one part to one function and one part to the other function, okay? So you redefine your F and your D in such a way that they contain one square root of the soft factor each, okay? If you only have one hadron in the final state, you are in a situation like this. And then the soft factor is there, it sits there, it is process dependent, so it has no relation with the soft factor that you had before, and there's no square root that you can make. I mean, you can take the square root, but then you have to square it again, and it sits there, and there's no way to separate it out. So the strategy we used was to redefine the fragmentation function, the one fragmentation function that we see, and say, let's keep the fragmentation function to be the collinear part of the process. And these, we keep it separate. And we sort of, we write evolution equation for it. We take care of it in a special way. We model the part of the soft factor, which are profoundly non-perturbative, and we deal with it in this way. But the idea is this, okay? So that in one case, you can use this strategy if you have, this is this, right? This is Drelian, and this is E plus E minus annihilation. The collinear parts can be different, but that you always have to. And so the strategy of the square root works. If you have 3, then you don't know what to do, right? If you have 1, you don't know what to do, and so on. 4, 5, 6, you have to reprove the factorization theorem each time. And my feeling is that the only way out is to to stick to what we did. So to stick to a purely collinear definition for your TMDs and keep the soft factors separated. But then, you know, life is complicated. Okay? Right, so are you ready for the picture? Yeah. Right, see you tomorrow then.